Hello student, so welcome to the Foundation of Classical Electrodynamics course. So today we have lecture 7 and we will going to learn the line, surface and volume integration. We have today class number 7. Okay, so last day we mentioned about the line integral, and if f is a vector field, say a function of x, y, z, some vector field, then the corresponding line integral we calculate like f dot dl some point a to b. So, today we will going to calculate for a given problem. So, the problem is the vector field f is given as, this is a vector field which is a function of x, y and z, and it is given as x square I unit vector minus x z j unit vector minus y square k unit vector. So, this is a vector field and the problem is this. This is a coordinate system, and in this coordinate system I am having a unit box. So, this is this point, let us call this point O, this point say A, and this point here it is C, this is B. These are the points A, O, C, B. Well, now I need to calculate this quantity. The line integral I need to calculate for the path, for a path which is closed. For path, the path I should mention, the path is A, O, B, C, A. So, I can show you the path here. So, the path is, I need to go from A to O, that is over this path, and then O to B, then I go from here to here, this path, and then B to C, go from here to here, and C to A. So, you can see that this is a closed path. So, that is why I can write a closed circle here. So, this is the this signifies that this integral is over this given closed path. So, my path is this and the vector field is given, and also it is given that this length of this section is 1 unity. This is 1. So, from here to here, okay, so my drawing is need to change to understand properly. Let me so from here to here this length is 1. So, this is a unit, all the lengths are 1. So, this is the unit length cube with side 1 unit. So, let us now try to calculate this integral. So, I can now, the first part is I can now divide this closed integral into 3 parts. So, the total integral can be divided into 4 paths rather. So, this is one path is a to b, from a to O, because my path is AOB. So, it is A O, then O to B, then B to C. This is my first part, this is my second part, this is my third path, and finally C to A. This is my fourth path. It is a 3-dimensional path. So, 2-dimensional problem are even easier. So, that is why I took a 3-dimensional path, so that you can understand that how. So, finally, I am coming from C point to A point. Okay, now one by one I just calculate. So, for that is all for path 1. So, for path 1, if you look carefully what information I get. For path 1, if this is x, y and z, for path 1 you can see that y is equal to 0. What about z? Z is also equal to 0. So, the expression becomes simpler. Only change is there is only change in x. So, x is changing from 1 to 0. This is the variation we are having here. So, for that, if I calculate my f first, so f simply it is given like x square x z. So, z is 0, y is 0. So, we simply have my f as x square I, that is all. So, and also x 0 y 0 mean dx dy equal to 0. So, f dot dl, this quantity is x square I dot dx I, because other terms are 0, y 0, and I should write here explicitly. So, dx is non equal to 0, but dy and dz, this is 0. So, this is simply x square dx. So, now if I integrate it from say 1 to 0, f dot dl, it should be integration of 1 to 0 x square dx, it should be minus of 1 by 3. Okay, that is for path 1. What about path 2? In path 2, if I look carefully, path 2 means I am going O to B now. Now, O to B, x will be 0, z will be 0. So, that I should write here first. So, my x is equal to 0, z is equal to 0, and y changes from 0 to 1. So, again I can have my f. So, if I go back to the expression, my f, y is non-zero. So, my f should be, so this quantity, and now I should write directly. So, for path 2, my f dot dl, this quantity gives me simply minus of 0 to 1 y square, and here you have to be careful because y is non-zero, but when you have f dot dl associated to y, we have dz. Okay. But here also dz is equal to 0. So, this quantity is eventually, even y is not equal to 0, but dz is 0. So, eventually this gives me 0 as dz is equal to 0, because there is no change in z, it is in y x y plane, over x y it is changing. What about path 3? For path 3, what we have, I can see that it is going from B to C. So, y value is 1, but x and z they are changing. So, for path 3 I have y equal to 1 and x equal to z, this condition I have. dy obviously it should be 0 and dx equal to dz, that is the condition. So, that means my f I can write it as x square I minus x square j minus k, because my x and z are same. So, I just replace z to x here. So, it is x square, this also become x square and this is 1. So, that is why it is simply this. Now, my dl, what is my dl? The length element, it should be dx I plus dz k dy is 0 here. So, f dot dl simply comes out to be, if I do that, simply comes out to be x square dx and then minus of dz, but dz and dx are same. So, I can have x square minus 1 dx as dx is equal to dz. Okay. Now, I am in a position to integrate, because I know what are the integrals. So, f dot dl for this path 3 should be equal to, y is changing, x is changing from 0 to 1. So, I just put 0 to 1, integral is, everything is in terms of x. So, I should not have any issue here, and the result is 1/3 minus 1, it should be minus of 2/3. Okay. And finally, for path 4, for path 4, what we are having? For path 4, if I check here, for path 4 I am going C to A, and when I am coming C to A, x value is fixed, it is 1, and y and z are changing, and then I should write that here my x is equal to 1, but y is equal to z. That means dx is equal to 0 and we have dy is equal to dz, that is the condition. And putting everything into f, I can have f is equal to I, because x is 1, minus z j minus y square k. And what is my dl? Dx is 0. So, I can have dy j plus dz k. Okay. Now, dy and dz are same, they are varying in this way only. So, eventually I have f dot dl is equal to minus of z dy minus y square dz, which is simply minus of y plus y square dy, because y and z are same. So, I just replace z equal to y and dz equal to dy, and then I am going to get this. The final thing is to execute this integration. So, for that I have f dot dl for that path. I should have the variation of y. If you look carefully, I am going from up to down, that means the variation of y should be 1 to 0. So, that variation I will put. So, variation is 1 to 0 and negative sign I already put here, and the function is y plus y square dy. If you execute, it should be half plus 1 by 3, absorbing this negative sign. So, it seems it is 5 divided by 6. Now, finally, I need to add all these paths. So, let us do that. So, this is for path 1, this is for path 2, this is for path 3, and finally, this is for path 4. So, when you calculate the total integration, it should be the integration for path 1 plus the value of integration for path 2, the value of integration of path 3 and 4. And now, I am going to put the value. So, for 1 it is minus 1 by 3, then plus 0, then minus 2/3 and then 5 by 6. These are the 4 values I figure out, and the value should be 1 by 6. So, the closed line integral value is eventually I find it is minus 1 by 6. So, this is the way, students. So, I am giving you a elaborate example with a relatively complicated path, but this is the way you should do. You just need to find out what is the path first, and then try to understand what is the relationship between x, y, z, so that you can integrate it. And a vector field is given f, and vector field means at each x, y, z points, the value of the field is given a vector, and that particular point it is a vector, a direction of a vector, and it changes and it forms a vector field. So, this vector field is given, and you need to integrate over a closed path, and this closed path is given here with this figure, and one by one you calculate and you figure out the value. Okay. The next thing is the surface integration. Surface integration. So, in surface integration, what we have, suppose we are having a surface here like this, and a section of the surface, tiny section of the surface we can cut, and a vector field is moving through this surface. Suppose a vector field like this is moving through this surface. This is a vector field, say A, which is moving through this surface. Now, this surface should have a direction. This is the unit direction of this surface, and this is my ds, the small amount of surface. So, the surface integral is essentially, if I now write mathematically, it is A dot ds. This is the value I want to find out. This is my surface integral, and normally we write S or double integral. Well, this is essentially the surface integral is A dot the unit vector that we have ds. This is the way also you can represent, because ds is a surface element with a unit and n is a unit vector. So, this is the way you can. Now, if the surface is closed, for example, we are having a closed surface like this, like a ball, and if I take a section out of this ball like this, where the field is moving like this, and this is ds, and this direction is the n unit vector of this surface. Now, for this case, the surface element, the integration of this thing is, say, this integration, say d psi is A dot ds. Now, if I want to find out the entire integration for the closed surface, then psi will be simply closed surface, that is why I put a close sign here, A dot ds. So, I will integrate the entire surface which is closing some volume. So, this is called the closed surface integral. Closed surface integral. Close means it is confining a volume. This confining a volume. So, the entire integration should be over this surface. And so, now let us consider a problem to understand how to calculate this closed surface integral. So, maybe I define a problem and then it will be easier. So, the problem is like the previous one. The problem is, suppose I am giving a surface is given like this. A block, maybe I can use this color. This is a surface, this is my x direction, this is my y direction, this is my z direction, and a vector field is given like the previous case. The vector field A, suppose, is given, and the vector field is 2 x z, an arbitrary vector field I am taking like this, plus say x plus 2 j plus y z square minus 3 k. And now, problem is you need to find out the surface integral for this given vector field for say 5 different surface. So, the 5 surface except the bottom, this is a problem given, I think it is given in Griffith's book. So, I am doing that. So, I can have 5 surface, one is here, another is here, another is here, another is here, and another is that side. These are the 5 surfaces, and you need to integrate. So, there are 6 surfaces, but you need to integrate the entire surface, the surface integral for these 5 surfaces. So, I am not going to do the calculation of all the 5 surfaces, it will be a lengthy calculation, but I can show you the technique to find the surface integral for a given surface, and I think that is enough. And also the information that is given is this length is from here to here, this is a block, and this length is 2. From here to here, this length is 2. So, this is a block of length 2. Okay. So, quickly I will do the surface integral among 5, I will do the surface integral for the plane where x is equal to 2. So, which plane I am talking about? X equal to 2, that means I am talking about this surface 2, what as per the figure. So, the surface number 2. Okay. So, for this is the surface where x is equal to 2, I am talking about this one. So, let me show you clearly. So, I am talking about the surface, this one, this is the surface, and I want to integrate this vector field over this surface. Now, what is ds, the surface element? First I need to calculate ds, the surface element is, since it is x equal to 2, the surface element should be dy dz, and the unit vector is along x. So, unit vector should be I. Now, this is a vector quantity. Now, A dot ds, if I calculate, it should be simply I 2 of x z and dy dz. Now, x is equal to 1 because x is equal to 2, that we know. So, eventually this value is 4 z dy dz, this is the value you are having. Now, you are in a position to integrate. So, now I need to integrate it over this surface. So, for surface 2, that is why I write it here 2, A dot ds will be simply 4, what we get, 4 integral of z dy z dy dz. So, I can write 4 integral of dy, dy is changing from 0 to 2, and dz is z dz, z is also changing from 0 to 2, because over the surface x and y and z both are changing from 0 to 2. And if you execute, you will find the value as 4 into this value seems to be 2, and this value is z square divided by 2, 0 to 2. So, eventually it seems you are getting 16. So, this is the value of one surface. Now, you are asked to find out the value of the other surface also, 5 surface, and also if you include the lower one, this surface, and integrate everything. So, you will going to get the closed surface integral. So, suppose you are having this surface as well and you calculate the entire. So, how you calculate the closed surface integral? Let me give you A dot ds. A is a vector field and you are asked to calculate the closed surface integral. The surface is given, this is simply a block. So, you one by one you should calculate the surface. There will be 6 surface. So, you calculate 1, then 2, then 3, then 4, 5 and 6. Then all the results you sum, and whatever the value you get, that should be the closed surface integral for this vector field where the surface is defined in this way. So, this is the way you can calculate the closed surface and also the other surfaces. I am just showing one example of one surface, which is surface number 2, but you can do the surface number 1. In surface number 1 you will have y is equal to 2, and then you go on, x and y is changing, and this is exactly the similar process you should follow. Okay. Now, finally, we have the volume integration, the volume integral. volume integration. So, volume integration, what you do, I can have a scalar field that can be integrated over a volume, given volume. In Cartesian coordinate, my dV is the volume element, and we know that this is simply dy dx dy dz, and t is a function of x y z, and here in this case this is a scalar field. Okay. I can show one example. For example, I can, so the volume and rho x y z, rho is a scalar field. This is the, say, density of a system with changing with x y z, and I want to find out what is the total value over a given volume, and whatever you are getting here is nothing but the mass. So, this is a very simple example where you are doing the volume integral, and this is your scalar field, which is density here. But in electrodynamics, normally we have the vector fields. So, this volume integral can also be treated as a vector field, treated in a vector field. So, A dot dV, that you can, so this is a is now, so not dot here because volume is a scalar quantity, I should not write it as dot, simply A dV, that is sufficient. But here important thing is A is a vector field. And we can integrate this, and the integration, if I do, I need to, because A is a vector quantity. So, the integration is essentially A x then dV plus A y dV plus A z dV. You can integrate in this way. So, quickly we calculate one problem. So, the problem, so we need to calculate the volume integral of for a given scalar field. So, scalar field is given like x, y, z is equal to, say, x, y, z square. This is also given in Griffith's book. So, now I need to calculate this over a given volume. That is interesting. There is a trick here, so please be careful. So, this volume element is like this, a prism kind of thing. Okay, so the length here is 3, from here to here it is 1 and 1. This is x, this is y, and this is z. So, over this given volume I need to calculate this. So, I need to calculate T dV here for this given volume. Okay. So, let us start how to calculate. So, it is x, y, z square, and the volume element I write, this is dx, dy and dz. Okay. Then I just write in this way. So, z is changing 0 to 3. So, I can extract these z square, and also I have two integration here, and but x and y are related. You can see that if y changes, then x is also changes. So, I need to first find out what is the dependency of x and y. So, if I draw here once again this stuff, then you can see there is a relationship going on, and that relationship is, this is y and this is x, and if I consider this, so 1 by 1 cutting is going on. So, that means x plus y is equal to 1. This is the relationship we are having here. So, that relationship we are going to use, and we use in this way. So, integration 0 to 1 for y, y is there, and x, in place of x I just integrate it like 0 to 1 by y, because x from here I can have 1 minus y, it is changing like that. So, that change I include here, it should be x dx, I first make integration over this, and then dy bracket close, and then over I will have dz. So, this is the way you should integrate. Let us do the integration then. So, 0 to 3 z square, 0 to 1, then y, and this integration becomes 1 minus y square with a half term, and I have dy that I execute first, and then I have dz. So, these things if I do, I will have, let us put this half outside, integration 0 to 3 z square, and that term, because z and y are independent. So, I can have like, after integrating this seems to be okay, I can directly integrate it. I do not need to put the integration sign because it is a simple function. So, it seems it will be simply, the first integration will be y square divided by 2, and then minus of 2 y cube divided by 3 plus y to the power 4 by 4 and 0 to 1. So, if we execute all these things, you will eventually find. So, this is half, this is 2 by 3, this is 1 by 4, and then whatever z cube by 3. So, eventually we will get the value 3 by 8. So, that should be the value of the the volume integral of this scalar field. So, we have a scalar field, we are integrating this over this structure, closed volume. Volume means it is closed, I mean there is no point to say closed volume over this volume element, and we will get the result like this. So, this is the way you should calculate the volume, but you have to be careful enough that what is the relationship between, for example, here x and y is changing. So, it is these things, this trick you need to consider when you calculate that. So, I insist you to please practice with different books. There are several books available for where you can calculate, where you can find this surface integral, line integral and volume integral. Practice that with this trick, and then you will find this easy to calculate. It is not that if the volume element is given in a regular form, it is much easy to calculate. Well, with this note I would like to conclude. Thank you for your attention. See you in the next class.